So today we are going to discuss the second subpoint from this unit number 5, whose title is Introduction to Irrigation Engineering and Study of Minor Irrigation Works. So the first part we have covered in previous lectures, and now we are going to learn about the minor irrigation works. So there are so many minor irrigation works. Out of that, for your study, there is a Bandara irrigation, Kolhapur type pier, percolation tank, and lift irrigation scheme. Now, the question is, there are the major irrigation schemes like the dam and canal system. So, why to go for minor irrigation? So, minor irrigation schemes are invented and they are implemented due to some of the limitations or what we can say demerits of major irrigation scheme. When we say major irrigation scheme, in major irrigation scheme, a large reservoir is there and water is stored for longer duration, and from that the water is supplied to the canal system. So that is a major irrigation scheme. It is a storage scheme. So the demerits of major irrigation schemes are when these schemes are implemented, a lot of area goes under submergence. The area which goes under submergence may consist of the valuable agricultural land or it may consist of the Gautan areas. A number of villages will go under submergence. So that is a big problem and there is a lot of resistance from the farmers for this project. The second important demerit is the cost of rehabilitation. When these villages are shifted to new location, their rehabilitation is essential. Means for them, it is the duty of government to provide a new land for the agricultural and to establish the new Gautan areas. And likewise, their rehabilitation is carried out. So rehabilitation cost is major in case of major irrigation project. The next demerit is the land acquisition. So as these villages are rehabilitated, so their land is to be acquired and there is a constant opposition from the local farmers for this project. So land acquisition also becomes a difficult task for the government engineer. When the big irrigation projects are implemented, they have to take the environmental clearance. For big irrigation project, it is essential to carry out the environmental impact assessment. Okay, in short, it is called as the EIA study. Whenever the big projects are implemented, so at first from the government authority, clearance is required for the project. And for that, they have to submit the EIA study, environmental impact assessment study for the project. Means when the project is implemented, so how much disturbance will be there for the ecosystem and for overall the environment. And based on that, the permission is given. So this environmental clearance is a big hurdle in implementing the major irrigation. And in minor irrigation schemes, such an EIA study is not required because here no area is under submergence or a very small area is under submergence. Now, when the major irrigation schemes are implemented, then these schemes are implemented for some states. Now, there is a Sardar Sarovar project. The Sardar Sarovar project is for 3 states. So, there is a dispute in between states regarding the distribution of water from that project. So, that is one of the drawback of major irrigation. Then major irrigation schemes needs more time for completion. And to implement major irrigation schemes, huge financial support is essential. So these are some of the limitations or what we can say demerits of major irrigation schemes. And hence, the government is now giving importance to implement the minor irrigations. So what are the benefits of implementing minor irrigation schemes? That the time required to complete the project is very less. So speedy completion of the scheme is possible. Then initial cost is also less as compared to the major irrigation scheme. Then to implement the minor irrigation scheme, there is no need of the extensive investigations and long time investigations are not essential. Then there is a flexibility in the project to locate the headworks. Headwork is what? Headwork is a regulating structure which regulates the flow of water. And if sufficient foundation is not available, then also these schemes can be implemented. And these schemes are environmental friendly that as the area of submergence is very small and they are not affecting environment in large extent. So due to these various benefits of minor irrigation scheme, minor irrigation works are implemented all over India nowadays instead of implementing big irrigation projects. Now for your study, now we are going to discuss about these four types of minor irrigation schemes. And based on these four minor irrigation schemes, generally question asked is either write a short note on percolation tank, lift irrigation scheme, Bandara irrigation, KTVL, or there may be a question explain in detail the construction functioning of percolation tank. Also state its merits and demerits. So likewise, descriptive question may be there. So you have to prepare these four questions. Out of these four questions, at least two questions are always asked in the final examination. Now, in the answer, what you have to write? You have to write about the importance of that particular MI scheme. Also, you have to draw the layout of that scheme. Then you have to write about its components and how it works, that is, its function. So it is expected in the answer. And the last point expected is what are the merits and demerits of each MI scheme. Now let us start with the percolation tank. So you might have heard the term percolation tank. Percolation tank म्हणजे आपण मराठीमध्ये त्याला पाझर तलाव असं म्हणतो. Okay, as its name indicates, it is a percolation tank. And it is a tank. Tank means what? It is a one small reservoir. And this small reservoir is created in order to percolate the water in the ground. Okay, and that's why it is called as a percolation. So these percolation tanks are constructed on second or third order springs. And these percolation tanks are constructed on the springs and they are generally constructed at the feet of the hills. Means they are constructed at higher elevation. The water is stored in a percolation tank and that water is allowed to percolate in the earth crust. So below the surface of earth crust, there is an arrangement of rocks. There are number of layers of soils and rock. And these percolation tanks are constructed on rocky strata. And not rocky strata, they are constructed on fractured strata. So if it is a fractured strata, if the strata consists of weathered rock, then only this percolation is possible. Now, if the strata is a strong, massive rock and it is not a fractured one, in that case, that water will be merely stored in the percolation tank and that water will get wasted due to evaporation. So, what is the requirement for the percolation tank? Location requirement. First point is it should be constructed on second or third order streams. Means it is not constructed on any river. It is constructed on tributaries of the river. They may be constructed on a big natural drain like a nala. And they are constructed means what? The dam wall is constructed in order to stop the flow of water so that a pool of water is created behind that dam wall. And in case of percolation tank, this dam wall is essentially earthen dam. Means it is a earthen embankment. And earthen embankment is constructed in its shape is trapezoidal. It is constructed across the flow of water. And behind that, a pool of water is created. Reservoir is created. Now, as this dam is constructed and water is stored up to a certain elevation, and if the water level exceeds this particular elevation, which may be considered as a maximum water level in the tank. So if water rises above the maximum water level, then that excess water should be drained out from that reservoir. And for that, the outlet structure is constructed, okay, which is just similar to spillway of the tank. And this spillway is provided and it is a masonry construction. Generally, it is a stone masonry construction. Now, the outlet provided in case of earthen dam is generally called as a waste weir. It is called as a waste weir, means excess water is regulated from this waste weir to the downstream side. The water is stored on upstream side and the excess water is regulated through this particular waste weir. Waste weir is nothing but it is an outlet to the percolation tank. Its functioning is similar to that of spillway, which is outlet in major tanks. Now these percolation tanks should be constructed on highly fractured and weathered rock. And there should be aquifer, which is having a good capacity to hold the water. It should have a good capacity to accommodate the groundwater flow. Now, what happens when this percolation is allowed? The water gets the water reaches to the groundwater to the downstream side area. Okay, to the upstream side there is a reservoir that water is allowed to percolate, and now to the downstream side the groundwater level in the earth's crust increases, and this raised groundwater table is after that tapped with help of either tube wells or open wells. So these percolation tanks are implemented in the drought-prone areas where the rainfall is less. So here water is stored in percolation tank. That water is allowed to percolate so that the groundwater level is raised, and this increased groundwater table is tapped through open well and tube wells. Open well म्हणजे विहीर, tube well म्हणजे bore. So this is the system of percolation. In percolation tank, the water is not conveyed to the field by means of canal or by means of pipeline. Okay, its purpose is only to recharge the ground aquifer and to raise the water level so that that water can be economically tapped by the farmers to the downstream side. So with respect to the command area, this percolation tank should be at somewhat higher elevation so that the water will flow through the aquifer towards the command area. Now the command area is to the downstream side of earthen embankment. So this is the general idea of the percolation tank. Now we are going to discuss about how the percolation tank is designed. So in the design of percolation tank, the first point is the selection of site. So as we have discussed, the second or third order stream or fourth order stream is selected as a site for percolation tank. Its location should be at the foot of the hill so that it should have a good command area. And it also should have a good catchment area so that the water will be gathered behind this earthen tank. Now, for planning of the percolation tank, at first the yield of the catchment is worked. Now we have studied unit number 1, 2, and 3, and now we know how the yield of the catchment is worked. Yield of the catchment means what? Yield of the catchment is nothing but runoff. So how much runoff is generated from that catchment in a year? So in that case, it is worked out how many times this particular created reservoir will be filled. And from the topo sheet, what is topo sheet? Topo sheet is a sheet used to find out topo sheet you have studied in second year surveying. Topo sheet is a map of the area which gives details of all ground features in the area. These ground features may be natural or not. So this topo sheet is preferred in which this natural ground feature, that is drainage lines, are shown on the topo sheet. So on the topo sheet also contours are there. So if we draw a line on that drainage line as a length of dam wall, then we came to know how much area of submergence is there. With reference to the contour on topo sheet, we can find out how much submergence will be. Then by constructing two graphs, which is called as a storage capacity curve and elevation capacity curve, it is possible to find out the storage capacity of this percolation. And from that, we can compute what is the total storage capacity of the reservoir, which is created by constructing earthen embankment. So these are the steps to design a percolation tank. So along with these steps, the next point is design of this particular earthen embankment. Okay, the previous steps are related to the planning of entire percolation tank. And now see, this is a cross section of the earthen embankment. Okay, so this is essentially a earthen dam, and the type of dam is zoned embankment earthen dam. This earthen dam consists of two zones. Here we can say there is an internal core which is shown by hatching. This is a trapezoidal core which is shown by hatching, and this is constructed with impervious clay. Okay, it is a impervious clay. Impervious clay means what? It is having less permeability. Okay, so this soil is used at the center. So this is the central core. And this central core is supported with the coarse material, pervious material. So the coarse material consists of voids. These voids are interconnected. So through this coarse material, water can percolate. And that's why this material is called as a pervious material. Opposite to that, in the core, this material is a fine material. There are very few voids, and it is difficult to percolate the water through this. So this inner core resists the percolation of water through the dam wall. Now this embankment is an earthen embankment. So when the water is stored against this earthen embankment, always seepage of water takes place. In order to check the seepage of water through the earthen embankment, this inner core is placed which consists of impervious material like clay. So clay consists of very fine particles. That's why whites are less. That's why its permeability is less. And that's why it resists the seepage. But it is not strong. And that's why to give support to this core, the supporting casing is provided, which consists of the pervious material. And these are the two main components of zoned embankment type earthen dam. And then to the upstream side, some protection is provided in terms of stone pitching. At first, a gravel layer is laid on the upstream side slope, and above that, the stones are laid. So that is called as a stone pitching. So the stone pitching protects the upstream side of slope from the wave erosion. When the water is stored, the waves are generated, and these waves may notch out the scoop of water, the scoop of earth from the upstream side slope. And if this continues for longer duration, then failure of embankment is possible. In order to save this embankment, this stone pitching is essential. Then one more important component of this earthen embankment is the drainage system provided to the downstream side of it. Okay, so there is the upstream side where water is stored, and there is a downstream side. So consider this particular downstream side too. So this is a downstream side too. And to the downstream side too, filter is provided. So what is the role of filter? So role of filter is to drain off the seeping water through the earthen embankment. The water which is seeping through earthen embankment is drained through this horizontal filter and this particular tap filter. So through this filter arrangement, the seeping water through the body of the dam is drained out so that there is less pressure developed due to the seeping water in the embankment, and embankment remains stable. So this is about the construction of earthen embankment for percolation dam. Now this earthen embankment, okay, so see the previous figure. So this is having the top bund level. I think there is a top bund level. So this is the crest of the embankment. So this particular point is the crest of the embankment. And at the crest of the embankment, water is not stored up to the crest. Okay, so this there is a some highest flood level. Okay, that highest flood level is mentioned. And there is a normal water level in the reservoir. This is the normal water. So the head from the normal water level to highest flood level. Okay, so that head passes over the waste layer. That is the outlet for the percolation. And above that there is a freeboard. So this freeboard facilitates the uh, uh, freeboard avoids the overtopping of water from the earthen embankment. If also the waves are created, then also overtopping is avoided. So that is the importance of term freeboard. Now, how the freeboard is decided? So the freeboard is decided with the formula 1.5 times HW, where HW is the height of waves generated. And for that formula is 0.014 into dm raised to 0.5. So what is dm? Dm is a fetch length. Fetch length means what? If there is a reservoir, if there is a earthen embankment, so suppose this is the earthen embankment, and behind that, this pool of water is created. So from this dam wall, what is the longest distance? So that is called as a fetch length. Okay, this is a fetch length. This particular is fetch length. So what is the fetch length? That is a DM, the longest exposed water surface on the reservoir, because this fetch length has a relevance related to the wind velocity. There is no obstruction to the wind along this fetch length. So if the fetch length is more, the wave height will be more, because this wind flowing over the water surface creates waves in the reservoir. So that is the importance of fetch length, and with respect to the fetch length, the height of wave can be calculated, and with respect to height of wave, then freeboard is decided with the formula 1.5 times the height of wave. Then the second point should be considered is the settlement of the embankment. So what kind of material is there and how that material is compacted. Based on that, the settlement of the overall structure takes place. So if the earthen embankment is normally constructed and hand compacted, in that case, the 10% of settlement is considered. So 10% extra height should be provided. So you are familiar with the term consolidation and settlement in geotechnical engineering. So when this earthen embankment is constructed, in due course of time, that consolidation and settlement is possible. So in order to tackle with this, the extra height is provided. And for that, these are the two guidance values that for hand compacted, 10% additional height should be considered. And for machine compacted, 5% additional height of the embankment should. Then how to compute the top width of the embankment? The top width of the embankment is calculated with the formula W is equal to H by 5 plus 1.5. So that W is the top width of the embankment and H is the total height of the embankment. Total height of the embankment is decided during the planning based on the topo sheet when we have to finalize what is the capacity of that particular tank. At that time, this total height of the embankment is decided, and with respect to that, the top width is computed. Then the length of embankment. Length of embankment again depends what is the topography of the area. Now, when we say length of embankment, then this embankment is at same elevation to the left bank and right bank. So consider the points which are normal to the drainage line and which crosses the same contour having same elevation. So based on these things, the length of embankment can be worked out. Then based on the type of material considered for the construction of earthen embankment, the upstream and downstream slope can be suggested. If the type of material is homogeneous, well-graded material, then you are familiar with the term well-graded soil. Okay? So if it is a well-graded soil, then it is upstream slope suggested is 2.5 as to 1 and downstream is 2 as to. If it is a coarse silt, we are familiar with the term silt as a soil. And if it is a coarse silt, suggested upstream slope is 3 as to 1 and downstream is 2.5 as. So likewise, this table provides information for deciding the sites. So we have discussed about how to decide freeboard, how to decide top width, how to decide height of embankment, length of embankment, and size. Now, next point is how to compute the peak discharge. So this peak discharge is important in order to design the west weir, that is the outlet of the percolation. So to compute the peak discharge, three methods can be used. One is a rational method, or it is called as a rational formula to calculate peak discharge, which is Q is equal to CIA upon 36, where Q is the peak discharge in Qmax, C is the runoff coefficient, I is the intensity of rainfall for a duration equal to the time of concentration of water swing. You are familiar with the term time of concentration. Okay. Then A is the catchment area of the watershed in hectares. So if we put all the values, we get peak discharge. Second is the Dickens formula. So Dickens formula is generally used for the catchments in North India, which provides the peak discharge. Formula is Q is equal to C into A raised to 3/4. So where A is the catchment area in square kilometer and C is the constant. And these formulas are empirical formula. Dickens formula and Rabbit's formula is the empirical formula. So these hydrologists have provided the constant value based on uh, the topography of the land. So they have suggested different values of C based on the different parts of the country. For Central India, C is 11.5. Sorry, for North India, it is 11.5. For Central India, it is in between 14 to 19.5. For Western India, it is in between 22 to 25. And there is a Ravi's formula. So Ravi's formula is considered for the catchments in South India. And here the different values for C are given based on the location of catchment area from the coast. If the location is 80 kilometers, for areas within 80 kilometers, the value of C is 6.8. And as the distance increases, this value of C increases. So these formulas are used to find out the peak discharge of the catchment, and based on that, the length of spillway is worked. So length of spillway, the term spillway is used in case of dam. So here the term west weir or surplus weir is used. So for small tanks, the height of flow over a weir is taken in between 0.3 meter to 0.6. And this level is known as the maximum water level. We have seen in the sketch during the pre-board discussion. To decide the length of surplus weir, the formula used is Q is equal to C into L into H raised to 3/2, where small h is flow height over the weir, L is length of weir, and C is the constant for broad-crested weir. So broad-crested weirs are the vertical drop type weirs where water overflows over these broad-crested weirs. Now, when this water overflows over the broad-crested weir, that water falls at the foot of weir. And at that point, the erosion is possible. So there is a need to construct a horizontal floor, and there is a need to compute the width of horizontal floor. So the width of horizontal floor to the downstream side is taken as 2 times d plus h, where d is the height of the drop wall, that is a vertical drop, and h is the maximum head of water over that weir wall. Similarly, after the end of horizontal floor, some stone apron, which is also called as a talus, should be constructed, and the length may be taken as 2.5 times of d plus h. Okay. So after the horizontal floor, which may be constructed with concrete, at the end of horizontal floor, then the rough stone apron, which is called as a talus, is constructed. The purpose of horizontal floor as well as the this talu is to protect the downstream side area of the west weir from erosion because water is dropping from certain height, so it may damage the downstream side area. So this is all about the percolation tank. And after the percolation tank, the next structure we are going to discuss is Bandhara irrigation. Okay, now our time for this particular meeting is over. So we will stop for a moment. Again, I will share your link. You please again join with me so that we can complete the remaining part. Thank you.